Welcome to Side of Science.
With Stacey and Clinton, because every story has a side of science.
On today's episode, we're talking about all things colour, paintings, pigments, peacocks and pyrotechnics.
Stacey, I have a question for you. What do ancient Egypt, Dr. Frankenstein and Van Gogh's Starry Night have in common? And I'll give you a hint. It is chemical and colour related.
I think I'm going to need a bigger hint.
It's definitely a tricky one. Okay, it's a good story, so I'll fill you in. So let's go back about 5,000 years to 3000 BC. It's ancient Egyptian time. They had actually created the first synthetic blue, Egyptian blue, calcium copper silicate, by grinding sand, copper, and essentially baking soda and heating it. And we see this a lot in Egyptian artifacts, this Egyptian blue coming through. The Romans also had the formulation from the Egyptians, and they called it cerulean.
Yes, Devil Wears Prada. We know cerulean. Yep.
It's not just blue. It's cerulean, exactly. So it would then be thousands of years before we see another synthetic blue. So formulation was essentially lost. So just to kind of paint the historical picture, in around 1500s, Michelangelo is painting the Sistine Chapel. He is having to use lapis lazuli as his paint pigment.
Pricey.
Worth more than gold, apparently, at the time. But it was the only way he could paint a blue sky, essentially, because there isn't a synthetic pigment available at that time. So the colour blue was highly prized across Europe.
Coveted.
Very coveted. So we jump ahead another couple of hundred years to around the 1800s, and we're in Germany now, and there is a alchemist, Johann Dippel, I think I'm pronouncing his name right, who is obsessed with making a fortune for himself. So he is drawn to alchemy with the idea of creating a lifelong elixir, which a lot of Europe was obsessed with at the time.
Still is.
Still is, right? Look at Instagram.
Yeah.
And he has created, by experimenting with cadavers and animal blood and human blood and all these gross things, he's created Dippel's oil, which he's selling as an elixir for longevity to the people of Europe. And he makes a decent fortune. And he's sharing his laboratory with a man who has makes his income from creating pigments. And one night he is creating a formulation for a very reliable red, and he accidentally uses some of the tools that are coated with Dippel's oil, and they wake up apparently to find this blue concoction.
Right. So the red has turned blue.
The red has turned blue, and they've suddenly synthetically created a blue pigment, which is then called Prussian blue.
Wow.
Right? And so they literally, since the Egyptians have created the first synthetic blue, they hold the formulation a secret, but it doesn't take long for other scientists to reverse engineer it.
Right.
They've made enough money, but we see it then appear, particularly in China, and it makes its way to Japan. It then becomes a pigment for a lot of the woodblock carvings, particularly Hokusai's wave, that famous tsunami wave, and then that eventually makes its way back, influencing European painting at the time, and is a big influence in Van Gogh's Starry Nights.
Wow, what a link.
What a link, right? It's a tale of three blues. And the real hook, I think, is that Johann Doppel was born, the castle that he was born in as a child, his family didn't own it, but he was born there, was called Frankenstein. And Mary Shelley happened to travel through that part of Europe around this kind of same time and visited the castle and heard of this kind of this crazy alchemist experimenting on cadavers. And there are some theories that led to her creating the story of Dr. Frankenstein.
Wow, so it's based on Dippel, and
potentially.
Okay.
As much as we can.
That rumor. Yeah.
Right, we'll start as much as history records will tell us. So I thought it was a great introduction to what we're talking about today, which is essentially colour.
It's fabulous.
And there's so much to talk about in this as we've found.
Yeah, well, I don't know where to start because there was so much in researching this. And initially I sort of thought, oh, okay, we can talk about this and that. But even just with the paintings, like in my research, I found out that later in life, Monet developed cataracts, and eventually he had to have surgery to remove the lens from one eye in what's known as a lens extraction. But the cool bit is, without the lens, Monet could actually see ultraviolet light. So ultraviolet actually translates to beyond violet. So we can't usually see it. The lens filters it out. But he was able to see it with the lens gone. And so after his surgery, Monet reported seeing colours differently. And he described things as more bluish or purplish, possibly because he was now perceiving these UV wavelengths. And so some of his later paintings, especially the famous water lilies, had a shift in colour palette. And he may have literally been seeing a different world.
Which is amazing, right?
Yeah.
And there's so much of what we're seeing here is the obsession or the drive of colour through human history, really. And obviously it's around us all the time in nature as well. So your story gives us a perfect segue to like what is happening with the perception of colour. Like, how does this work? Let's go back to that. Let's go back to the basic science of it and the physics of seeing the colour.
Good word, perception, because, it's how our brain interprets lights of different wavelengths. So we have a spectrum, and the visible light spectrum is what we as humans can see. And this is between 380 to 700 nanometres. So the blues are shorter wavelengths, and then the reds are the longer wavelengths. And then obviously we see green as well in the middle. So we have rods and cones in our eyes. So rods don't see colour. They just see light and dark. And I don't know if you've ever gone out stargazing at night, but if you look from the corner of your eye, it's usually easier to see the stars more clearly.
I've never tried that.
Oh, that's because the rods are actually at the sides of your eye, and so they pick up just the gradient. But the cone's in the middle, and so you have 3 cones. S cones will pick up those shorter blue wavelengths. M cones for medium, the green wavelengths, and then the L cones, long, for the red wavelengths. And so we only have 3 cones for these 3 colours, but the wavelengths that hit them and turn these cones on, they will actually combine and subtract different colours so that we can make more colours. A bit like how the printer works. You've got your 3 colours, but they'll mix to give you colours that aren't actually in the spectrum.
Do you know how many colours we can see?
I think that's probably subjective. I think if you ask different people, they'd have a different answer. There's lots.
I did Google it, and they estimate it's around 1 million.
Wow.
But there is a condition called tetrachromacy, which a small percentage of women have, but it is about 12% of the population apparently, where they may have a 4th type of cone, allowing them to see potentially up to 100 million colours.
Yeah. It's wild, isn't it? And we would never be able to, like, I was looking at this as well, and you can't even mimic that. Like, you can't put special goggles on and colour the world the way that a tetrachromat would see it. So tetra being 4, chromat being colour. So we're trichromats because we have the 3 cones. And then you get dichromats as well, which are people, I guess, who are more colourblind, and also a lot of animals. And they mostly see the world in yellows rather than the reds. The reds and greens are harder to distinguish for the dichromats.
I am colourblind, and it is green, brown, blue, purple. So I certainly long for a pair of goggles. If someone could invent that I could put on and see the world as colour.
How did you find out?
It's not you get told. I got told in primary school. It wasn't a great experience. You basically do the test, and then you get a letter saying these are the jobs you can't do. And I was like, oh, surprise! So
that's why you're not a pilot.
That's why I'm not a pilot, literally.
Yeah, but you wouldn't know any different. And you always look well coordinated, so it hasn't impacted your dress sense at all. all the millions of colours of the world, and all we seem to do is argue about whether the dress is blue and black or white and gold.
Absolutely. So let's go back to the painting, Starry Night, and the blue pigment, whether it's lapis lazuli or cerulean or Prussian blue. How are we seeing this? What chemically is going on for us to see this blue colour?
Okay, so the colour is determined by the pigment's chemical structure and how that interacts with light. So transition metals and organic molecules often make strong pigments, so things like iron and copper. And the arrangement of electrons in the pigment molecules influence which wavelengths of light are absorbed.
So before you said there's 3 main wavelengths, blue being the shortest and red being the longest.
Yep.
So the chemical structures of these molecules essentially are interacting differently with the wavelengths of light, and it's reflecting back to us differently?
That's exactly right. So if we think about paint pigment, it's actually subtracting colours. Okay, so we've got our primary colours of cyan, magenta and yellow, and the pigments work by absorbing, so subtracting, certain wavelengths and reflecting others. So if we're seeing a blue, it means that it's actually reflecting blue wavelengths and our eyes perceive those, and it is absorbing red and green.
That's because light, sunlight or artificial light, has all 3.
Yes, well, sunlight is the addition of all colours of light to make white light, and sunlight is white light.
So it comes down through the window of the museum, hits Van Gogh's painting. The painting subtracts
Yep, absorbs
red and greens.
all the colours of the rainbow except for the wavelength we actually interpret and see.
And I'm getting reflected back the blue in this instance.
Yep.
Great. That's a good explanation. When we flip it to, say, producing light, it's the opposite, right? Like we're starting with black rather than white and we're adding colours in.
Yeah, so if you think of light through a prism, so think of the album cover. Yeah, okay.
Got
so
it.
you've got the split of the colours of the rainbow. So that's white light coming through and refracting so that you have all of those wavelengths bending and you can see them. So to get white light, all of those colours, the Roy B. Gibb of the rainbow, red, blue, they actually combine as to one to make the white light.
And
so it's the all of the addition of colours.
so in this, it's an additive. And this is how we have screens. Our phone screens, our TV screens, our computer screens, they are, as I understand, little LEDs or little lights that produce the different colours.
Yep.
But if you have them all switched on producing everything, they're going to be white.
White light, yep.
And if you turn it off, your TV goes black.
Yep.
Good summation.
Yeah. So we talk about TV screens using light, but that wasn't always the case. You remember those old TVs, like massive TVs?
I'm too young to remember, Stacey.
You might remember
Don't laugh so hard.
more from TV shows.
Yes.
Yeah, okay.
Yeah.
So they used an electron gun to fire a beam of electrons at the back of the screen. The inside of the screen was coated with phosphor compounds that would glow or emit light when it was hit by the electrons. And this is how the image was created. The magnetic fields steered the electron beam line by line across the screen to paint the picture. What's interesting, though, is I don't know about you, but I used to sit in front of one of these TVs from an early age, cross-legged and, hooked.
And they would hum and fuzz.
Yeah.
So they were very like you would be drawn to them.
Yeah, it was, well, actually, when electrons are fired at very high speeds, they can create X-rays when they hit solid material. And so TVs, electrons weren't as energetic, but at high voltages, tiny amounts of X-rays were accidentally produced.
From the TVs we're watching.
Yeah.
Which brings us almost back to Monet and his vision impairment, because the X-ray waves are sitting outside of the visible light spectrum, further to the left, as I understand it, than ultraviolet light, but in that same
Yeah, so when we talk about light, it is, especially the spectrum that we can see, that is a small portion of the electromagnetic spectrum. So visible light is in that, and then ultraviolet light, so beyond violet that we can't see, is not visible. And X-rays are just, again, to the other side, to the left of that. So we can't see those either, but we know that they can be damaging.
So if Monet's impairment or surgery had been more extreme, he may have been able to see through walls.
That's probably a leap.
But I went there.
Yeah.
Does that mean, I do have a question though, does that mean that when we think of, say, X-ray, then ultraviolet, that blue is like the first colour we can see? Like it's, because it's the longest wavelength as we think about that wavelength getting more intense?
I think actually, so the shortest wavelength is violet, and we can see that a little bit, but our eyes are less sensitive to it. And so blue is actually the first wavelength that we really pick up in terms of the shortest, and then the longest. So along that spectrum, you've got your sort of blue, green, yellow, orange, and then red is your longest.
That's where ultraviolet comes from. Mm-hmm. It goes from ultraviolet to violet.
Yeah, exactly.
Penny just dropped.
So beyond violet, we can't see it, yeah.
Amazing.
Important note, whilst we can't see ultraviolet, there are animals that can. So sharks actually navigate using UV light, and bees use it to find flowers. And then many fish, reef fish, like the damselfish, have skin patterns visible only in ultraviolet light. So it's used for communication and mate selection, but it's like a private channel for fish. They can see it, but other like predators and things can't. And what's really interesting is the way that colours behave underwater is different as well. So if you've ever been to the Great Barrier Reef, have you ever snorkeled and seen it?
Yes.
And did it marry up with the Attenborough documentaries you'd seen on the Great Barrier Reef?
For a start, he wasn't there.
Okay. Disappointing.
And yes, the colour is much more... I mean, I was snorkeling, so I imagine going down closer it might be better, but it's quite dulled out.
It is. And I think a lot of people are disappointed when they first see it because you are sort of expecting these vibrant colours. But water acts like a filter and it absorbs light, but not all colours equally. So red, orange and yellow, those longer wavelengths, they're the first to get absorbed by the water, and so we can't see them. So as soon as you go sort of a little bit underwater, red colour disappears. So fish that are red when you're snorkeling will appear like a grayscale. Same with the corals. Bright red corals you can't see. And so when they actually take those documentaries and photographs, they're putting that white light underwater in close proximity so that it will then reflect back.
So it looks much more vibrant, whereas if it's me snorkeling, the sunlight is being filtered out, so I'm not getting that same vibrancy.
Exactly.
Is that why then that when you say take a fish out of a water, like I've seen those documentaries where the fish is taken out of the water, the colour of the fish lifted out of the water looks so different?
Absolutely, yeah. So there's some theories that a lot of deep sea fish will be red to hide from predators, and exactly that. Like blue colour is, you can see the deepest. So like a bright blue Lynkia lavigata starfish, sea star, you can see those really clearly. They're really nice colours because they're blue and it's the short wavelength that it doesn't get filtered out as easily.
So we've talked about colour pigmentation, how we see colour, how we produce colour, particularly again through pigmentation and chemical processes and how that's acting differently for it to be visible to us in different colours. Colour has been around us forever. Humanity has been inspired, essentially, trying to recreate these colours through the pigmentation and dyes. Yeah. What's happening in the natural animal world around us that's colour related? Like how does these principles apply there?
Well, it's funny because you think of a peacock and it's not dyed that colour, like it's naturally that colour. So the structural colour is not caused by pigments or dyes. Instead, it comes from the physical structure of a surface. And so these are microscopic patterns that interact with light. So tiny structures can bend, scatter, reflect, or interfere with those lights those light waves in really specific ways, and so only certain colours can reach your eyes.
Which would mean then that, for example, and I'm not suggesting this be done, but if you were to take peacock feathers and grind them up, you're not going to produce a blue colour. But you can do that for some insects, because I know in the Egyptian example when we started that they did use shells to create certain pigments, so they must have a chemical in them versus what you're saying is a structural component, which is just reflecting light differently.
Certainly. So like your carrots have beta carotene, which is an orange pigment. And if you can extract the pigment out of that. Same with leaves. Like chlorophyll is a green pigment. And so you can grind, or spinach juice is going to be green because of the pigment. But in terms of things like butterfly wings, peacock feathers, some fish scales, and even soap bubbles, that's just to do with the manipulation of the light waves from these structures.
Awesome. Okay.
So speaking of carrots, I'm not sure if you're aware, I guess now at the store you can get different coloured carrots. So there's purple, white, and then orange. The orange ones have been the major kind of carrots that we've had because the royal family in the Netherlands, the House of Orange, way back when, they selectively bred carrots to be orange.
And that must have become popularised in Netherlands and then obviously spread across.
Through, yeah.
Which is interesting example because we've talked already about the link between culture and colour through creating pigmentation. But here we've got an example of the influence of natural colours in biology and the link to culture and how that then spreads.
Yeah. So they selectively bred them so that, orange is the major colour.
I have a question. We've talked a lot about colours, different colours, perception of colour. What is the advantage to us and other animals even perceiving colours?
Yeah, it's a good question because you have a lot of like vertebrates and things that actually can't see colour. They just see, I guess, the absence of colour, so shade. And so if there's a shadow coming over them, like a clamshell will shut up so that it's protected itself. So in terms of where colour and being able to see colour evolve from, I think there's still a lot of debate or unclear about it. But the fact that there are so many different varieties of colours, so the fact that I can see, well, I hope I can see most colours, but I'm here and could survive to reproduce, but then so can somebody who is colourblind, then there must be a benefit to both, essentially. So in New World monkeys, for example, the gene for red-green cones is on the X chromosome. So if we think about males, they have an XY chromosome, so they can only get one copy. Whereas females are XX chromosome, so essentially they could get two copies of this. If you get one copy, you can only see your dichromat. You can only see sort of the two colours, the colourblind. If you get two copies, so most of the girls can be full colour. They're trichromats. Does that make sense?
Yeah.
So looking at what this means for the monkeys, the trichromatic females may be better at spotting ripe fruit or young red leaves, which are higher in protein, and that leads to better nutrition and higher survival. But what about the males? Well, they're better at seeing shapes and borders and can spot insects that camouflage well. So they don't have the colour differentiation, but their sense is heightened, and so they can pick out the insects. And so they found this out because they were looking at their waste, their fecal matter, and doing diet studies. So that was really interesting.
So what you're saying essentially is that there is no real right and wrong when it comes to colour in the natural world.
Yeah, with evolution, there never really is. It's just a trade-off. Yeah, and it's working for both of them. So it keeps going.
Keeps going. So
let's finish with a bang. Let's talk about fireworks and the different colours of fireworks. Okay, so fireworks starts with combustion. So when a firework explodes, we have black powder or gunpowder inside, which ignites the energy needed to heat everything up. That heat excites electrons. So the combustion releases a huge amount of heat energy. The energy is absorbed by metal salts. So the different metals like strontium, copper, sodium compounds that are packed inside the firework. These electrons, they jump and fall. So in these metal atoms, the heat causes the electrons to jump to a higher energy level. So when it combusts, that electron gets excited by the heat, it jumps up. But they don't stay excited, and everything that must go up must come back down. So they fall back down to their original energy level, and when they do, they release energy in the form of light. And it's that light that we see as the colour. So the amount of energy released when the electron falls back down dictates the wavelength and therefore the colour of the light. So strontium will give you red, copper, blue, sodium, yellow, and so forth. And because metal atoms have loosely bound outer electrons, they're really easily excited by the heat and emit light at very specific, predictable wavelengths. So you can arrange your fireworks show.
And everyone's oohing and ahhing.
Yeah.
But it also goes back to what we talked about before with that the wavelength, the visible wavelength, but also that additive component in that we're now getting essentially light produced against a black sky, just different colours based on the different arrangement of electrons in the compounds, which isn't very dissimilar to what we talked about when we talked earlier about even just a reflection of, say, the sunlight off the blue painting.
Yeah. So here we're getting a chemical reaction through the combustion to get that energy. But yeah, all the wavelengths, all light we see is a wavelength.
Perfect. That's a good finish. So how do we bring this all together for teaching?
I don't know where to start with this. There's so much. I guess if you're studying Frankenstein in English,
absolutely
you could
start there.
Yeah.
Ancient Egypt in history.
That's it. And then you've got your chemistry. So talking about the fireworks and the flame tests, that's essentially the same thing.
Students love that.
Yeah, wavelengths of light is physics and how the different colours work or how we perceive them. The eye in biology, so the rods and the cones, but also the genetics that's in that.
And of course, art. Back to where it all began with the Starry Night and the pigments.
Yeah, and Monet.